Well, good morning. Today is the last lecture of this course. We'll finalize the part on architectural evaluation and about scenario-based evaluation. Basically, I will explain the software architecture analysis method, which is also the approach that you will need to use in the project. This was the issue last week. Architecture is very important. It has the largest impact on the software development project, on the life cycle. And so implementing the architecture costs lots of resources. So it is wise to evaluate the architecture early on and not later on. Otherwise, we said we will just have damage control. So we have to analyze the architecture early on for system qualities. We can predict, if we do it early on, the quality of system before it has been built. We can evaluate and we can identify potential risks. Okay? This was the issue that we discussed last week. We said there are several architectural evaluation techniques, among which scenario-based analysis is a practical and very often used approach, easy approach. This is the method in general. So we have stakeholder criteria. We derive the criteria from the stakeholders. The quality criteria relate to the stakeholder concerns. A scenario-based evaluation approach means that we need to define scenarios. On the other hand, we have the architecture design, and actually we check the architecture with respect to the scenarios. So this is the evaluation method. If the architecture is okay means with respect to the quality criteria, then we can implement the architecture. Otherwise, we need to redefine or refactor. Okay? And we said this redefinition can mean also that you need to redefine the domain, the problem, the stakeholder concerns, etc. So, is there any systematic method for scenario-based analysis approaches? Because last week we just discussed the concept. What is a scenario? What type of scenarios do we have? How should we write scenarios, etc. Indeed, there are actually plenty of research on this issue. Many different related scenario-based architecture evaluation approaches, which you can find in this paper, in IEEE Transactional Software Engineering. This is the set that is described in this paper, but there are also other approaches besides of these. Basically, so SAAM, Scenario-Based Architecture Analysis Method, which is the method that I will also explain. SAAM CS is more for complex scenarios. SAAMI for extending SAAM by integration in the domain. SAAMR for reusability. ATAM is actually a more sophisticated approach in which they try to define the trade-off analysis. Okay, when we consider multiple quality concerns, for re-engineering, for prediction of maintenance, etc. Okay, so in general, most of these methods are somehow based on this SAAM, which is somehow a kind of the core of these scenario-based architecture analysis approaches. Plus, SAAM is said also that it has been evaluated using industrial projects. Okay, so it's more mature, we could say, in that perspective. This is the method. So the paper in which the methods are applied, defined, explained. What is the SAAM? It's quite easy actually. It consists of 5 steps. This is also the process that you will need to apply in the project. First, you describe some architecture or candidate architecture. So you could analyze actually one architecture or multiple architectures together. Okay. How do you do that? You develop scenarios. So architecture description. You develop scenarios. How do we develop scenarios? As we said, we can hold a workshop. Invite the stakeholders, let them describe scenarios, do brainstorming, reuse scenarios. So we collect all these scenarios based on the stakeholders' concerns. Once we have these scenarios and we have the architecture, the third step, we can start the architectural evaluation. Okay. We perform scenario evaluation. So actually in the third step, we take one scenario and we check, we analyze whether the architecture meets that scenario. Okay. The fourth step, review scenario interactions. I will explain that in detail, but then we actually look at the other side. We look at the architecture components and check how many scenarios interact, as we say, in that architectural component or module. These two evaluations provide you some insight in the quality of the architecture, and in the fifth step, therefore, we can provide general overall evaluations and provide some feedback, some hint for refactoring, etc. So let's look at this approach in more detail. The approach is explained in this paper from Rick Kazman about Bas Clement's scenario-based analysis of software architecture, IEEE software. In this paper, they use this case study. It's a revision control system. So it's for configuration management, where you can check in files, check out files, edit files. Okay, so it create releases, backup to old versions of files, etc. Okay. For the particular case, there was no documented system architecture prior to the evaluation. That could sound strange, but this we can see also now and then in organizations. They have some software, but no architecture yet. Of course, no architectural description. We said every system has an architecture, okay, whether it's explicit or not. The purpose in this particular case was to evaluate whether they should go on with the existing system, whether it's stable enough with respect to the oncoming future requirements. Okay. So they want to assess the impact of anticipated future changes. This part is actually important, the part on the purpose. You always analyze an architecture for some purpose, okay, for some goal. In this case, it was for whether the existing system is stable enough for the future changes. You could also have an existing architecture and then see whether it's stable enough. So you should make it explicit. So this was clear in this case. First step. Identify the alternative architectures. In this case, there was no architecture, as we said, but so they had to reverse engineer the architecture or define the architecture. This is the architecture as is given in the paper. The details are not that important, but as we said, an architecture consists of a set of modules and relations among these modules representing the gross level structure of the system. Here we have the elements are components and cause relation. Well, this is just one particular view of the architecture. The details on whether it's right or not, it's not important for our purposes to show evaluation. So we have some architectural description. Okay? Well, second step is quite easy. Develop scenarios. Develop scenarios that the system must support. How? By actually talking to stakeholders, like as we said, holding a workshop, brainstorming. So in that case, so we try to capture all important scenarios. And scenarios should represent the tasks, concerns relevant to all important stakeholders. Okay? So if you would, this is an important step here, if you would miss some scenarios, then actually the evaluation would not be really sound or not valid, because you would have missed some important issues that you had to evaluate. Okay? So we try to define as best as possible, to drive the important scenarios and not miss anyone. So for that, we have to, as we said, we have to identify the stakeholders. Actually, in normal case, we already have these stakeholders. If you would have designed the architecture, right? But in this case, we didn't have the stakeholders yet, so there was already a system. So in any case, whether it's designed or not, the scenarios should reflect the stakeholders' concerns. Who are their important stakeholders? As we said, you should not look at persons physically, but roles that need to be played in the system. So a stakeholder is some role that is fulfilled. So typically you should say, what are the existing roles in this system? What is their interest? Once you know the roles, you find the persons behind these roles, you interview these stakeholders, you iterate until you have sufficient coverage. Of course, you are never sure that you have sufficient coverage. Okay? It's just like the principle of testing. You just test whether the system will fail or not. Okay? But if you do it thoroughly, at some point you could say, okay, now we have sufficient set of scenarios which reflect to a large degree the concerns of stakeholders. We might have missed one, but we believe that we have a solid set of scenarios. Okay? Then you start the evaluation. So we could have, so we said scenarios should reflect the stakeholder concerns. So we identify the stakeholders. In this case, we provide here 3 examples. A user, a maintainer, administrator. There are 3 important stakeholders in this case. A user is the end user who checks in files and out, etc. For the user, there are 2 scenarios. Okay? Compare binary file representations. Okay? Typically an end user concern. You have a revision control system, okay? And you have different files. You would like to compare binary files. Configure the products toolbar. Okay. So how do you derive this? Typically by actually interviewing these users. Okay. The second stakeholder is maintainer. Maintainer looks at from different perspective to the system. Is it maintainable? So a typical scenario, port to another operating system. That's the scenario. So what's the impact of this scenario on the system? Make minor modifications to the user interface. Administrator, change access permissions for a project. So you have different users. Okay, you would like to change the access permissions. So can we do that? Is it possible? Integrate with a new development environment. Okay, so just set of stakeholders. For each stakeholder, you define these scenarios. Well, then we are in the third step. We have the architecture. It's well documented. It's described, and we have the scenarios. Once we have these 2, we can start the scenario evaluation. The process here is quite simple. What's the what do? We just take one scenario and we check the impact of the scenario on the architecture. The impact is defined in two ways in SAAM, Software Architecture Analysis Method. Scenario can be either direct or indirect. Direct scenario means that the scenario can be executed by the system without modifying the system, without modifying the architecture. Okay? Say it's the scenario is direct. Oh, we can just do that. An indirect scenario requires some modification to the system. Okay, you say scenario is either direct or indirect. If scenario is indirect, it can mean to the addition, removal, or update of an architecture component or relation. Okay? You have to change something to the system. So the system cannot cope with these indirect scenarios. Of course, whether a scenario is direct or indirect depends on both the architecture and the scenario itself. So if you have two different architectures, a given scenario could be direct for one architecture but indirect for the other. This is again the example in the paper. We have these 6 scenarios. These are these 6 scenarios, the user, maintainer, administrator. The users had the scenario compare new binary file representations. So what do we do in this case? We look at this scenario. We look at the architecture, and then we define the evaluation. Is it direct or indirect? Here they have decided that it's indirect. And this is the explanation. This scenario requires the modification to diff and physdiff components. Okay? You take the scenario, you say, I cannot do this scenario. To execute this scenario, to do it, to realize it, I need to change the diff and physdiff. Okay? It's just very simple analysis. Second scenario, again from the user, configure the products toolbar. Here they say direct, which means the system can execute it. Here they don't have an explanation, but equally you could also provide an explanation. It is direct because it's fulfilled by these components. Okay. The third and fourth scenarios are from the maintainer. Port to another operating system. Scenario, architecture, you check. You say, oh, I cannot do this. You say indirect. For example, in this case, there's the explanation. All the components that call Win31 must be modified. This is a pretty old paper, so Windows 3.1 operating system. And in the architecture, it appears that some components are just related to this operating system, so it's not independent. And here is the evaluation. Porting to another operating system means that we need to change the main, physdiff, and controls. Okay, etc. Fourth scenario, make minor modifications to the user interface, indirect. This will change to one or more of these components, which call the Win31 API, specifically main, diff, and controls, etc. Okay? Just the same process, just by pulling through these scenarios. Scenarios, and then you characterize these scenarios. Is direct or indirect? It's clear? Okay. So we already here have some characterization of the architecture. Okay, we already know about how many scenarios are direct or indirect. This provides already some hint about the stability of the architecture. In the fourth step, we look not from the scenario perspective, but from the component perspective, architecture component. this is actually followed. There's a causal relation. You first do this step, and then you can do this step, because in this step you look at each architectural component and check how many scenarios interact in that component. The scenario interaction here is defined as multiple indirect scenarios that affect the same component. For example, we have this component, and these are the scenarios which impact, which require some changes to this component. Then we say these three scenarios interact at this component. Okay? So then in that case, SAAM also defines the notion of good scenario interaction and bad scenario interaction. Good scenario interactions are those interactions in which all the scenarios are semantically related. Semantically here means that they relate to the same concern. For example, all concerns relate to security, and they all impact one component. We say these are good scenario interactions because they only relate to one concern. In addition to that, we could have bad scenario interactions. Then that's the case in which the scenarios are not semantically related. That is, they are not related to the same concern. For example, in this case, if these colors represent different concerns, we could say security, recovery, concurrency, and it appears that they all impact the same component. This is a bad scenario interaction, and the reason for characterizing as bad is that there's somehow some poor separation of concerns. You have one component, but it appears that multiple scenarios of different concerns impact the same component. So the component is not well separated. Okay? This is already some poor separation of concerns. So let's elaborate on that a bit. What is separation of concerns? Actually, there are two important issues here. Cohesion, and coupling. That's the next slide. Cohesion relates to single modules. So here we have two situations. This is one module or one component which addresses three different concerns. We say this component is less cohesive. Why? Because it can fall apart easily. Why is that? Well, if we need to change one of these three concerns, just one of these trees, we have to change that component. This is a case where we have separated these concerns to different modules, and where every module addresses just one concern. Then we say here, these modules here have high cohesion. Because its cohesion is just one task. They just perform one task, one concern. Okay? It's a very important principle in software engineering. What is our goal actually? We have to maximize cohesion within a component. The higher the cohesion is, the better it is for our system. Because if there are some required changes, they can be easily localized and will not propagate. Okay? We have to change synchronization. In this case, we just need to change this component. We have to change it here. We have to change recovery, we have to change this, authentication, change this. But in this case, it's just like the concerns which needs to be changed. We can identify the module, and that module is changed. Okay? Cohesion. The second principle in separation of concerns is coupling. This is a general software engineering principle. Actually, when we design systems, we have to aim actually for loose coupling. That is, the components that we have in our system, they should not be just arbitrarily coupled. So you should only provide the necessary couplings. In that, here are three examples to show what coupling means. This is a totally uncoupled system. We don't see that also often, but if we have some change here in some component, it will not propagate at all. It will just be here. This is a highly coupled system. There are many dependencies. If we need to change to some component because of the couplings, we will have the so-called ripple effect. A change will trigger another change requirement. Okay? So this is bad. This is a loosely coupled system. There are some dependencies, obviously just the necessary dependencies. If there is some change, it might impact some components, but not as much as here. So we should aim for minimizing coupling between architecture components. This will reduce complexity and reduce ripple effect. Actually, the scenario-based analysis also somehow provides an indication about this cohesion and coupling. Okay? Because if we have many scenario interactions, if we have at some components multiple scenarios interacting, it indicates that that module is not cohesive. Okay? If scenarios, these multiple scenarios are distributed over all the components, then we have actually some coupling in these components, and this provides some indication about lack of separation of concerns. So how do we define these scenario interactions? How do we represent these? It's quite easy. The first one is tabular representation. We just list the components, module X, module Y, and we define the number of changes to that component. Well, component X requires 3 changes. Component Y requires 1 change. Just tabular. Or the second approach is a graphical representation, in which we provide a so-called fisheye view. Here the size, the number of changes, impacts the size of the view, as we will see in the next slide. Actually, this is the first tabular representation. These are the modules in our system, and here we put the number of changes. This already, so this evaluation provides us some characterization of the quality of the architecture. In particular, it shows here us that for the given set of scenarios, this main WRCS, the hook, and the festive and controls are components with the largest scenario interactions. Okay? Somehow, so this gives us the set of sensitive components. For this set of scenarios, these components are sensitive. Okay? We could represent this also in fisheye view. So here we have WRCS is the largest, so therefore this is the size is also larger. It's just for visual, it provides more visual representation. Here we see directly which is the most sensitive components. So what should we do if scenarios interact? Scenarios could be all of the same class and relate somehow cohesion. Scenarios could be of different classes or relate to different concerns. Then we should check whether the component can be subdivided. Okay? If 3 scenarios interact at some component, it might be that the component consists of 3 submodules, in which each submodule addresses the different concern. I think that's the second case. The third case, scenarios are of different classes, relate to different concerns, and it appears that the component cannot be easily subdivided. So this is some hint about that the architecture is not well designed, or there's not even the component itself is not well structured. Well, altogether, we generate the overall evaluation. So what does the evaluation consist of? You say this is the architecture, this is the stakeholders, we derive this set of scenarios, and it appears that you give the tabular representation. These components are centered, we have the largest impact, largest number of interacting scenarios, okay, etc. So you provide just some, you state the list of architecture problems. You say, well, for this scenario, we have to do too many changes. That's bad. So this is a key. Porting to another operating system takes us too much effort. Okay, or changing the communication protocol, the concurrency protocol, or in this case the versioning management, whatever, takes too much effort or not. We can cope with these scenarios. It appears that our system architecture is quite stable. So in this particular case, it was the decision either to go or not to go with the same system. So should we just continue with the same system or develop a new system from scratch? So and that this decision can be typically supported by this whole architectural, scenario-based architectural analysis. So it's a quite easy, simple, but very practical approach, which is also used a lot, I can say a lot, so because it's easy. You don't need to define the simulations, you don't need to define a prototype, no difficult mathematical formulas, but here you just say scenarios. You just describe scenarios. And the advantage is also that you also invite all the stakeholders and somehow also cover the related concerns. Okay. I'll just give another example to show the process again. The window management system. This is an example of window management system, simplified, consists of 4 components. Event manager for I/O controlling, process manager for scheduling and managing application processes, screen manager for maintaining integrity of screen, and window manager for managing the windows that are related to application processes. We define the architecture. Okay, typically could just a very simple architecture consisting of a set of modules and relations. Second step, we develop the scenarios. We see here 20 scenarios, okay, based again on the stakeholders' concerns. We define the stakeholders, the scenarios. Okay. The third step, we do the analysis. So there we define the impact of each scenario on the architecture. This is the scenario. So we start with this scenario. We check is direct or indirect. Actually, that's the decision that we make, and we do that for all scenarios. In this case, it appears that this part, the first 10 scenarios are direct, and these are indirect. For example, here, monitor activities of the user, scenario 16. This is indirect because there's no monitoring about monitoring concern in this architecture. So we can say it's indirect. For system to command-based operation system. Here we check, we know the system, we can say it's indirect. Resize the window, well, it's just done by window manager, done. It's direct. Terminate the process, interrupt the process by process manager, etc. So there's of course some subjective evaluation there. Somebody has to decide on whether it's direct or indirect. And that somebody is typically the architect, but supported by, for some stakeholders, developers, for example. Okay? And they say, is this direct, yes or no? So that you provide the evaluation. this indirect scenario, so impacts several components. So we perform scenario evaluation. The failure occurs and the system shuts down. It appears that this scenario impacts two components. Okay, which means then these two are indirect for this scenario. Port system to command-based operation system impacts all components in this case. Okay. It's just similar to the revision control system, the same process. Well, fourth step, reveal scenario interaction. This is the result of this case. Again, so remember then, the third step, we look from the scenario perspective. We take scenario and then check which components it impacts. The fourth step, we look at each component, okay? Each architecture component, and then check how many scenarios are interacting in that component. Like here, so the window manager, there seems to be about these 5 scenarios are interacting. In this case, we have also provided the scenarios which are direct, okay? Which means for the given scenario, we don't need to do anything in this component. Etc. So this is the scenario-based architecture analysis method. What we do is quite simple. You can do it also in the project. In the project that you have to apply, you should apply this to the module view. Okay, as we said, you look at the module view and then check the impact of the derived scenarios on the module view, and then identify some direct scenarios, some indirect scenarios, and provide hints. But there's lots of research on software architecture analysis methods. Actually, if you look at these methods, we can just reflect on that. There are some positive points, but there are also less positive points. So what would you say about the positive points? Actually, I have explained, but can somebody say what is positive here? Just 2-3 points. Easy to apply. Just you can start directly if you have the stakeholders. Right? That's maybe the okay, easy to apply, but another. It's an easy approach, and we can apply it for different kinds of applications actually. We could apply for embedded systems, for telecommunications, enterprise applications. It doesn't matter what the kind of application is. It's just quite easy. Just define the scenarios. Okay. You involve multiple stakeholders, etc. What is less actually? What would you say?
If you forget some scenarios, it won't be a good.
Okay, that's implicit. So it also the method itself is also doesn't guarantee that you have identified all the scenarios. Okay, that could be a limitation. So I could put that in the. It's interesting. What happens if we don't identify? How does it address multiple quality concerns? This method. So we just actually check whether it's direct or indirect. What does it mean? Okay, whether it's adaptable or not, right? How can we cope, for example, with reliability in this approach? Recovery. Okay. It doesn't make explicit statements about that, but the point is the SAAM is actually in particular for modifiability actually. Okay? For a given set of scenarios, do we need to modify the architecture or not? It's simple, but at some parts it could be limited. If you want to have specific reasoning about some quality concern, I would like to reason about whether my system is reliable or not. That is in a specific sense. But here, it's not easy to describe this as a set of scenarios. So unfortunately, we don't have time to explain the other methods. Actually, the reason why there are other scenario-based architecture analysis methods is also that to complement this approach. They still also have these steps, but they also provide additional steps to define, to cope with, for example, complex scenarios, to cope with reuse, to cope with failure scenarios, okay, etc. Let's just summarize. So the summary, we have architecture, very valuable artifact, but also very important artifact. It's the earliest artifact in the software development life cycle after the requirements. If the architecture is not stable, it's bad for the project. Okay? So we should evaluate the architecture early on, and for that we have different techniques. In particular, we have seen that we can use scenario-based analysis techniques, which is an easy and practical approach to evaluate this architecture. Any questions? This is clear, I hope. Okay, let's break. Second part, we just summarize and provide exam guidelines. Okay.